Okay, so reabsorption and filtration or secretion, which are essentially synonymous once we're passed into the renal tubule. If we're filtering something into the renal tubule, into the filtrate, at that point we are secreting it. It is destined to end up in the urine. So the difference between these. So reabsorption. This is where something, substances, water, ions, nutrients in some cases, are going to move from the filtrate into the peritubular cells, so they have to cross the cell membrane there. Then they're going to go from the cells, out of the cells, across the cell membrane on the other side into the peritubular fluid, and then diffuse into the peritubular capillary, so into the blood. So in a nutshell, we are moving things from the filtrate back into the blood. So we don't want to urinate them away, we're trying to bring them back, we're trying to keep them, hold on to them. Filtration is the opposite, or secretion, because it's going to end up in the urine. Here we have substances, ions, things like that, moving from the blood, so from the peritubular capillaries, going into the peritubular fluid, then into the peritubular cell, so across the cell membrane, so into the cell, and then across the other cell membrane on the other side into the filtrate. So it's going to end up in the filtrate and eventually be in the urine. So that's why we can also call that secretion. So we already know that to move things across the cell membrane, which we had to do to get it into the cell and then to get it out, whether it's going from the filtrate to the blood or from the blood into the filtrate, we have to cross the cell membrane 2 times in order to go across both of those sides of the membrane. So we know that we need to have carrier proteins for most ions to cross a cell membrane. So we can have active transport where we use ATP to move ions across the cell membrane. That would be when they're moving against their concentration gradient. So you need to use energy to pull them against their will in a way. They have no force to go into the cell or out of the cell, so you're going to either push or pull them in the direction that they don't want to go. Now, when we don't need to use energy, so when an ion is moving with its concentration gradient or with its electrochemical gradient, we would call that facilitated transport or diffusion, facilitated diffusion. So we have a carrier protein that is just open and it allows something like, say, sodium to move into the cell. And that's important to remember, back to AMP1, that we know that sodium pretty much always wants to go into a cell. If you keep that in the back of your mind, it's going to make this next part a whole lot easier to understand if you just follow the sodium and know that it wants to go into the cell. Now, with facilitated transport, we are not typically going to be moving just, say, sodium. Like in the nervous system, we saw sodium leak channels, and it was just sodium moving into the cell. Or we had potassium leak channels, and it was just potassium leaking out of the cell. Both of those moving with their gradients. In the case of the kidneys, the transport proteins that we're going to be looking at are going to tend to move more than one ion. So sometimes those ions will be moving in the same direction, and sometimes they'll be moving in opposite directions. So maybe one's going into the cell and maybe one's going out. So if they're both going in the same direction, that's called co-transport or symport. Those 2 words both mean the same thing. Only one of them has to be moving with its electrochemical gradient. That provides enough energy to pull the other one with it, even if that second one isn't moving with its concentration gradient. And this doesn't have to be only 2 ions. It can be 3 ions or even 4. So we'll see examples of both of those situations where we have 3 or 4 moving all together in the same direction in co-transport or symport. Now we can also have the same situation where we have a carrier protein and an ion is moving with its gradient either into or out of the cell, and then another ion is moving in the opposite direction. So if one is going into the cell, the other one's going out of the cell, and vice versa. And that's called counter-transport or antiport. So they're just moving in opposite directions. And again, only one has to be moving with its electrochemical gradient. The other one could be moving against its gradient. As long as one is moving with its gradient, that'll work. And this would also, we could apply co-transport and counter-transport to active transport as well, just using energy instead. So you already know an example of a counter-transport, active transport mechanism which would be the sodium-potassium pump, pumping sodium out of the cell in the way that it doesn't want to go, pumping potassium into the cell at the same time. Potassium doesn't want to go that way. That's countertransport. They're moving in opposite directions, but it's also active transport because we're using energy. No, we're talking about water because a big part of your kidney function is to reabsorb water to put the water back into the blood. So water is able to pass across cell membranes in the peritubular cells using just osmosis. So going according to osmotic forces. There's going to be a little bit of help here in the form of something called aquaporins. Aquaporins are essentially like little carrier proteins but for water, and they just make it much easier for water to pass across the cell membrane. So the more aquaporins you have, the easier it is for water. One little note about aquaporins is that ADH, so antidiuretic hormone, which we know from our endocrine system unit way back when, feels like a year ago now, but we know that ADH helps you reabsorb sodium and water to raise your blood pressure. But one of the mechanisms that it works using is that it helps the distal convoluted tubule make more aquaporins or express more aquaporins. So if you have more aquaporins, it makes it possible to reabsorb more water. So it makes it more permeable to water. Without ADH, the DCT isn't really permeable to water. That's going to come in handy in a few minutes in the next video, the third video. So remember that ADH makes the distal convoluted tubule permeable to water, and without it, not really permeable to water. Also remember that water is pretty much going to be following sodium because sodium is a big determinant of osmotic force. So when you reabsorb sodium, water is going to follow that sodium, so you're reabsorbing water. That is what we're going to get into, is how we reabsorb sodium, which is how we reabsorb water, which is a big purpose of the kidneys, regulating your blood pressure in this way. Now the last way that we can move substances, not across cell membranes, but between cells, is something called solvent drag. So this is taking not the route through the cells, but something called the paracellular route, which means between the cells rather than through the cells. So some water is going to be being reabsorbed that way, and some small solutes are able to, there's an ant, say hi to the little ant there. So some very small solvents are able to just kind of go with it, with the water between the cells. So magnesium does this to a small extent, phosphate to another extent. So this is not a major way that we'd be reabsorbing substances, but it does exist. So if we think about each section of the renal tubule as an overview, and what is getting reabsorbed and what is getting secreted in each section. So let's start with the proximal convoluted tubule. Here we're going to have a lot of sodium reabsorption. We're going to get into the exact mechanisms of how we do sodium reabsorption. Don't worry about that yet, we're going to get there. But just generally speaking, we're reabsorbing sodium, which means water is going to follow. We're actually going to be reabsorbing about 80% of the total water that we reabsorb in the renal tubule, in the proximal convoluted tubule. So a lot of water reabsorption happening here. We're also doing glucose reabsorption. We have little glucose carriers in the proximal convoluted tubule that enable the glucose to be reabsorbed. So that's where we should reabsorb all of our glucose that got filtered out, because we don't want to urinate away glucose. Now, occasionally, let's say you just have a lot of glucose in your blood. Let's say you ate an entire birthday cake, or in my case, the cookies I made yesterday. So I would have a lot of glucose in my blood right now. So in that case, a lot of glucose gets filtered into the filtrate and first running through the proximal convoluted tubule. So you have this whole lot of sugar essentially going into the proximal convoluted tubule, and you only have a certain amount of these glucose carriers that can help you reabsorb the glucose. So not all the glucose is going to be able to fit through a carrier. Some of it's going to end up just passing through the tubule and ending up as urine. If it's just a transient situation, so in my case, I ate a lot of cookies and possibly then ending up with some glucose in the urine, that's okay. It's a sign of diabetes if a person were to have consistently glucose in their urine, because that would mean hyperglycemia all the time. So having a small time period where you have a little bit of glucose in the urine is not so bad. Having it constantly, that is a sign of a condition. Now another thing that we'll be reabsorbing here is sodium bicarbonate. Oops, forgot to put the H there. So sodium bicarbonate reabsorption. Think back to bicarbonate. We're going to revisit that whole bicarbonate buffer system in a couple of minutes. But we're reabsorbing bicarbonate in that way to interact with the sodium bicarbonate buffer system, which is how the kidneys help to regulate your pH. We're going to get there in a bit. Now, moving on to the loop of Henle, the 6 segments, both in the descending limb and the ascending limb. We're going to have sodium reabsorption, chlorine reabsorption, and potassium recycling. So we're reabsorbing sodium and chlorine. This potassium recycling, we're reabsorbing it, but then putting it right back into the cells again. And we'll see how that works in a couple of minutes. So we're essentially having potassium move from the filtrate into the cells, back into the filtrate, into the cells, back into the filtrate, into the cells, over and over and over again, just moving it around. And this has a purpose. It's interesting how this works. We'll see that in a couple of minutes. So down to the bottom of the loop of Henle, the thin segment, only water is being reabsorbed here. We're getting about 15% of our water reabsorption from the bottom of the loop of Henle there in the thin segment, and that is a good amount of water reabsorption still. So remember, 80% in the proximal convoluted tubule and 15% in the bottom of the loop of Henle in the thin segment. So a good amount of water reabsorption happening here. Okay, now when we move up out of the loop of Henle, we're in the distal convoluted tubule. And here we're going to be doing sodium reabsorption still, chlorine reabsorption, potassium recycling. You'll notice that these 3 are the same in the 6 segments of the loop of Henle and in the distal convoluted tubule. They're using the same 2 carriers that are responsible for all 3 of these things. So we'll see those doing the same thing there. Water reabsorption, 5%, so not much, but still, makes a difference in how much water you're reabsorbing. And remember, this is dependent on ADH. So if you don't have ADH present, you won't get that last 5% reabsorbed, so you would just urinate away 5% more water there. The distal convoluted tubule is also where you have drugs and toxins being secreted. So let's say it doesn't have to be bad drugs. It could be, say you take a Tylenol because you have a headache. That's going to be processed, removed through the distal convoluted tubule, because you don't want to have the Tylenol in your body forever just because you take it once, right? And then also calcium reabsorption or secretion. This depends on hormones. So which hormones are present? So let's say you have a lot of calcium in your blood, so you don't want to reabsorb too much calcium. Calcitonin is the hormone for that. Oops, I'm pointing to the wrong thing. You don't want to reabsorb it, so calcitonin would cause you to secrete more of the calcium because you have enough calcium or too much calcium in your blood already. If your calcium is low, you do want to reabsorb it. So parathyroid hormone helps you to reabsorb the calcium to keep whatever calcium you have. You don't want to urinate it away if you don't have enough calcium. And then finally we pass into the collecting duct. Here we're doing sodium reabsorption and potassium secretion. No more potassium recycling. Now it's time to just get rid of the potassium here. And we're also going to be doing some more bicarbonate reabsorption. So again, back to the bicarbonate buffer system. And we're trading it for a chlorine in what we call the chloride shift. Okay. So, before we get into the exact mechanism of how we accomplish all of this, so we're going to look at all the carriers that are responsible for this stuff. And I know that looks like, oh no, that's a lot of carriers, but we're actually only going to look at 7 that accomplish most of these things. So it's not so bad. But before we get into it, I want to introduce to you the idea, I hope this all fits on here, it does, of the loop of Henle, countercurrent multiplication, and the medullary concentration gradient. This is one of the slides that I was talking about in the first video, that if you read it, maybe this is one that you might not have understood quite so well, because it's a bit complicated. So we're going to explain it here. So just follow along. Hopefully it makes sense. I'll explain it a couple times in a couple different ways so that it does make sense. So what we're looking at here is just the loop of Henle. So we're just focusing on the loop right now. So we're ignoring the proximal convoluted tubule and the distal convoluted tubule for right now. So we have the descending limb with a thick segment, then there's a thin segment at the bottom, then the ascending limb with the thick segment that's going to go into the distal convoluted tubule. So if you notice the filtrate, it's going down here and then it's going up here. So they're going in opposite ways, down, up. That is countercurrent flow of the filtrate. So not the multiplication part yet, but just the countercurrent part. Just means opposite flow, like a two-way street. Then we add in the vasorecta. Remember we talked about the vasorecta before. The vasorecta is a capillary and is flowing down towards the medulla. So that is also flowing countercurrent to, oops, not to that one, to this one, right? So it's going opposite to the ascending limb. So that's also countercurrent. Now what happens here? Remember that we have sodium and chlorine being reabsorbed, but we also have potassium. We're going to throw this in. It's something called the NAK2Cl carrier, and that's happening over here too. That means that we are taking out of the filtrate sodium, potassium, and, oops, 2 chlorines. Okay, so the NAK2Cl carrier is a co-transport mechanism where we take sodium, potassium, 2 chlorines out of the filtrate into the peritubular fluid. Now, potassium recycling. We're going to take potassium and put it back into the filtrate, and we do that as a counter transport mechanism with sodium. So here's a co-transport mechanism here. Here's a counter transport mechanism. And this will be happening over here too. So sodium going into the peritubular fluid, potassium going back into the filtrate. Okay. So same thing happening on both sides of the thick segments. So we have sodium, potassium, and 2 chlorines going out of the filtrate, ending up into the peritubular fluid, but the potassium isn't going to be in the peritubular fluid really. It's going to end up going back into the filtrate. So potassium goes out of the filtrate and then it goes back into the filtrate. That's the potassium recycling that I was talking about, going out of the filtrate and into the filtrate over and over again. So potassium is just going to end up still in here, okay, for the most part. That leaves, out of this carrier, that leaves sodium and chlorine. So we have reabsorbed sodium and chlorine. It's going to get picked up by the vasorecta. So sodium and chlorine on this side too, going into the vasorecta. So all kinds of sodium and chlorine ending up in the vasorecta. The vasorecta flows down, brings with it that sodium chlorine. There it goes down here. And it's going to start to get pretty concentrated down here and diffuse outwards. Just put a whole lot of sodium and chlorine. And if you think about what sodium and chlorine are, they are salt, right? So we're making it super, 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 super salty down here in the medulla, because remember the medulla is down here where the thin segment is and the cortex is up here. So we're essentially taking sodium and chlorine out of the filtrate. We're recycling the potassium, so we don't need to think about potassium anymore for right now. But we're reabsorbing that sodium and chlorine, taking it in the vasorecta and pulling it down towards the medulla, where it's going to just be super, 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 super salty. So to give you an idea of how salty that is, down here in the medulla, this number up here, there's the ant again. So this number here, 300 milliosmoles, is the osmotic pressure, or the osmotic force of the filtrate and the peritubular fluid up here in the proximal convoluted tubule. These are, this number is isoosmotic to your body fluids, meaning that your body fluids are in general about 300 milliosmoles. And that, of course, varies person to person, from hour to hour, but that is about your typical osmolarity there, 300. Now as you go down here, all this salt that you have just kind of pulled out of the filtrate and condensed in this one little area down here in the medulla has made it so salty that it is about 1200 milliosmoles. So super, super salty, right? This is what is called the medullary concentration gradient. It just means that you have a high osmotic concentration in the medulla around the thin segment of the loop. So really, really salty around that thin segment in the loop of Henle. That's the medullary concentration gradient. Now, what that does is it pulls water right out of the thin segment, because we remember that only water can move across the simple squamous epithelium here. This essentially watery fluid with some ions in it, yes, but it's, you know, a liquid water, like salty water, but still water. It's super, super salty around it, so that salt is going to pull the water right out of the thin segment. That's why we reabsorb about 15% of our water down here, because of this medullary concentration gradient. Now, as we pull the water out of the filtrate, what we're leaving here, we still have water in there, yeah, but we have less water because we're taking a lot of water out of the thin segment here. So we're just left with ions. So we're concentrating the filtrate as we go up here into the ascending limb. And as we bring this like concentrated, so a lot of sodium, potassium, and chlorine going up into the ascending limb and hitting the thick segment, now we allow those ions to move, and they are just going to have a really strong gradient to move really, really, really strongly out of the filtrate, because it's so concentrated that they're just going to want to get out of there. So that's going to step up this carrier a lot, like a whole lot, which is going to cause more reabsorption of sodium and chlorine, which will get pulled down here, make this saltier, causing water to get pulled out, making this more concentrated, making this more active, stimulating this even more, and so on and so on. This is a positive feedback loop, and that is what countercurrent multiplication is. Just having the water being pulled out of the thin segment, making this more salty, more concentrated, more hyper osmotic. As it goes up into the thick segment, which makes that carrier more active, which causes you to reabsorb more sodium and chlorine. Of course, the potassium just gets recycled, so we don't need to think about that one for now. And then that sodium and chlorine goes down, which pulls more water out. That is the positive feedback loop that is called countercurrent multiplication. And it keeps and maintains, sets up this whole medullary concentration gradient. So these are dependent upon each other. So if you just think of it, now that you know all the little bits and pieces, you have just sort of like a normally concentrated filtrate, just the same osmolarity as your normal body fluids going down here. You're pulling ions out of it, and it's going down here, and it gets super, super salty down here. So you're pulling water out of the filtrate, making this very hyperosmotic filtrate, very, very concentrated as it goes up here. And then you give it carriers and allow those ions to move out. So they're going to want to move out because you've made it super salty. You've increased their gradients. Out they go. We recycle the potassium, but the sodium and chlorine, we don't recycle that. That ends up in the vasorecta, gets pulled down here. So that we have this medullary concentration gradient to pull the water out and make it more hyperosmotic, more concentrated, to keep this carrier going. Okay, so another thing that is happening, as we take all that sodium and chlorine out of there, actually two things are happening. We're losing ions from the filtrate as we go up. So the carriers are going to start, way down here. So we're losing ions, losing ions, losing ions the whole way up. So as we go up, we are becoming more diluted. So this can also be called the diluting segment of the loop of Henle, because we start out super, super concentrated. That stimulates the heck out of these carriers. So these ions are going out, out, out of the filtrate, leaving just kind of, less ions in the filtrate, just more water, less ions. So we're diluting it, and we're actually going to end up hypoosmotic to our body fluids, to about 200 milliosmoles by the time we reach the distal convoluted tubule. So that's one thing that's going on. We're diluting. Now another thing has to do with this potassium recycling and also the loss of chlorine from the filtrate. So we're putting potassium into the filtrate. So that's a positive ion. We're taking chlorines away from the filtrate, and literally taking them away. They're not coming back. So we're removing negative ions. So you take away a negative, that leaves a positive situation. You put in a positive, that's a positive situation. That leads to something called the lumen positive electrical potential. What that means, now the ant's on me. Not going to kill him. So what that means is that it is positive charge in the filtrate. So the lumen is the inside of the filtrate as we go into the DCT. This positivity is going to help us reabsorb things like calcium and magnesium because it's positive. Those are positive ions, and the more positive charge you have here, the more the easier it is to move a positive ion out of that area. So magnesium depends almost entirely on the lumen positive electrical potential to be reabsorbed. Calcium, now we can actively transport that if we have, say, parathyroid hormone active, which causes us to reabsorb it. So calcium doesn't depend quite as strongly on the lumen positive electrical potential, but it helps. Okay, so I know this video is the longest video in the history of mankind, but we have more to do for it. So going back to here, we need to think of how we accomplish these things. How did we move these ions from the filtrate into the peritubular cells and then out the other side into the blood, or vice versa? How did we move them from the blood into the peritubular cells and then into the filtrate? So what are the exact mechanisms we used in order to move these ions across the cell membrane? And there are only 7 of them. So these are listed a couple of times on your slides just because it is a little bit, hard to remember, I guess. So I just wanted to really keep hammering away at this. But you'll notice that you'll see these a couple of times. But what we have here would be the filtrate. So the green in the center is the filtrate. Out here, this would be peritubular cells. I just put that there just to be the other side because we know that the peritubular cells would be wrapped around. And then we have peritubular cells here, and this is the side that I chose to put all the carriers on. And then we have the peritubular capillary. The peritubular fluid is just kind of like in there between. We're not going to mess with that. We're just kind of worrying about the cell membranes here. So look at the peritubular cells, and I just kind of drew one big long cell just to make it easier. But we have these peritubular cells here. There's a cell membrane in contact with the lumen of the tubule, so where the filtrate is. And then we have a cell membrane that's in contact with essentially the peritubular capillary. So the peritubular fluid and then the peritubular capillary. So we have a membrane on this side, we have a membrane on that side. So we need to move things across both membranes if we want to get them from here to here, if we're secreting or filtering, or if we want to get them from here to here if we're reabsorbing. Now these membranes have names. The one in contact with the filtrate is called the luminal membrane, and the one in contact with the blood on the other side is called the basolateral membrane. So what I want you to do here is focus on the sodium, because you know sodium's electrochemical gradient is to move into the cell. So if you just focus on the sodium and think of where it wants to go, into the cell, versus where you're trying to get it, because we know that sodium doesn't exist in a high concentration in the cell typically. It's going to be higher concentration outside the cell. So the cell is going to not want to have all that sodium inside. So keep that in the back of your mind. It's going to make life a lot easier. And we'll focus on the sodium, and we'll start at the luminal membrane. So we have three ways of getting sodium out of the filtrate and into the cell at the luminal membrane. So these little boxes are representing carriers, whether they're co-transport or counter-transport. Co-transport means they're all moving in the same direction. Counter-transport means they're moving in opposite directions. So let's take this one. We have our sodium in the filtrate. It's going to use this carrier. Sodium moves into the cell. That's with its electrochemical gradient, so that's happy there. We're trading for a potassium, so we have potassium inside the cell. Potassium is moving out of the cell. That's also with its electrochemical gradient, so that's happy. No energy required, just a basic facilitated diffusion in a counter-transport kind of way, right? Moving in opposite directions. Now we know that typically cells have more potassium inside, less outside, not so much sodium inside, but a lot of sodium outside. So this cell isn't going to be super happy about the situation of not having a lot of potassium and having all this sodium being reabsorbed. So keep that in the back of your mind as we move to this next carrier here, which is the sodium and hydrogen countertransport. Same idea, sodium moving from the filtrate into the cell, hydrogen moving from the cell into the filtrate. This would be with the gradient as well, at least for sodium. It kind of depends with hydrogen, but definitely for sodium. So this again requires no ATP. We're just having a counter-transport mechanism here, facilitated diffusion. Now here's the NAK2Cl carrier that we talked about in the loop of Henle, and also we have this in the distal convoluted tubule. This is co-transport, all three moving in the same direction. Sodium's moving with its gradient into the cell. Potassium is moving against its gradient into the cell. Chlorine doesn't really have a gradient into the cell or out, doesn't really care which way it's going. It's not typical for there to be a lot of chlorine in the cell though, so keep that in mind, but chlorine's just kind of along for the ride here. So we're having these four ions moving together, one sodium, one potassium, two chlorines, all moving together, co-transport into the cell. So we just took sodium from the filtrate, put it into the cell. At the same time, we lost some potassium to the filtrate, we lost some hydrogen to the filtrate, and then chlorine is also going into the cell, and some of that potassium going back into the cell. There's some potassium recycling right there. Potassium going into the filtrate, potassium going into the cell, into the filtrate, into the cell. Potassium recycling. Okay, so what did these carriers leave us with? They left us with a lot of sodium in the cell. That's not normal. They left us with a lot of chlorine in the cell. Also not normal. So how are we going to deal with that? We've also had a loss of potassium too, by the way. We'll deal with the hydrogen in a second. So let's deal with the sodium. We want to get rid of the sodium. We want to get the sodium out of the cell. So we're going to move the sodium out of the cell. That's not with its gradient. This is going to have to require energy. This is going to be active transport. So we're moving sodium and we're moving potassium. Actually, it's 3 sodiums out, 2 potassiums in. This is our sodium-potassium pump that we all know and love. Moving them against their gradients, it's rectifying the situation where we got sodium inside the cell. The cell doesn't want that, so out goes the sodium. 2 potassiums getting pumped in to replace the potassium that's getting lost to the filtrate. We'll ignore these for a second. We'll come back to them. Over here, the sodium and chlorine, we have too much sodium, we have too much chlorine in the cell. We want to pump them out. Sodium moving against its gradient, chlorine, doesn't really care which way it goes. So this is going to be another active transport mechanism pumping that out. So what we've done, if we just follow these 3 and these 2, so we've got these 3 at the luminal membrane, these 2 at the basolateral membrane. In all situations, we have taken sodium and taken it from the filtrate, put it into the cell. Then we've taken the sodium out of the cell and put it into the blood. We just reabsorbed sodium. Water's going to follow in both steps, so water's just going to follow that sodium. We reabsorb sodium and water, we raised our blood pressure. So that would be the job of ADH and aldosterone to stimulate these things. So ADH and aldosterone, well, they're both going to stimulate that one. They're both going to stimulate that one. Aldosterone also stimulates this one. So this has to do with the bicarbonate buffer system. It's sodium reabsorption, but it's also acid-base regulation. So let's just put that equation, and change colors here just to make it easier to see. So water plus carbon dioxide, this should look super familiar to you from before, gives us carbonic acid, which dissociates into bicarbonate and a hydrogen. And remember, if we have a lot of free hydrogen in our blood, we are acidic. And if we don't have a lot of free hydrogen in our blood, we would be more alkaline or basic over that way. So hydrogen is an acid or makes you acidic. Bicarbonate, however, soaks up the hydrogen. It binds the hydrogen, moves the equation that way. So that would cause us to be more alkaline. So if you are acidic in your blood, you want to get rid of hydrogen. You want to remove the hydrogen from your blood, put it into the filtrate, urinate it away. You also want to reabsorb bicarbonate. Remember renal compensation from months ago. This is the mechanism by which this is going to happen. So let's follow these 3 carriers now. Sodium going into the cell from the filtrate, just like always, doesn't require any energy. Trading it for a hydrogen. Hydrogen's along for the ride. It might be going with its gradient, not necessarily. So we're able to get rid of hydrogen that way. Hydrogen's in the filtrate. It acidifies the urine. That's fine. It's going to get urinated away. Okay, so we have sodium in the cell, of course. We can get rid of it in these 2 ways, but we can also get rid of it in this way because the bicarbonate buffer system, all of this, can happen within the cell. It also happens out here because remember that this whole equation is facilitated by an enzyme called carbonic anhydrase. And that is present in red blood cells. We saw it in red blood cells. It's also present in the peritubular cells and also to a small extent right along the luminal membrane inside the filtrate. So you can have the the bicarbonate buffer system happening a little bit here and inside of here. Okay? So wherever we have, carbon dioxide, which we do inside of cells, and we have water obviously, so we can have all of this occurring here and here. And of course out here, because that's the blood, and that's where we learned it originally happening in the red blood cells. So when we have the bicarbonate buffer system working, we have not just hydrogen, but we have bicarbonate as well. So we want to get the bicarbonate from the cell into the blood because let's say we're having an acidic situation, so we want to soak up that hydrogen so we're not as acidic. So we have 2 ways of getting the hydrogen into the blood. This one happens only in the proximal convoluted tubule, and this one happens in the collecting duct. So here, sodium moving from the cell into the blood along with 3 bicarbonates. Sodium moving against its gradient, so that's not going to be simple diffusion. It needs to take a little bit of energy to do that, those bicarbonates going along for the ride. So only in the proximal convoluted tubule. Out here in the collecting duct, we're not worrying about sodium at all. We have no sodium happening here. We just have chlorine moving into the cell, and we have bicarbonate, one bicarbonate in this case, moving out of the cell. This is called the chloride shift, which we mentioned earlier. Or it's also called the hamburger shift, after the person who discovered it. Okay, so to summarize this whole bicarbonate buffer system thing, if we are acidic, too much hydrogen out here, we want bicarbonate to soak it up, right? So we would do more of this. So we reabsorb more sodium, get rid of more hydrogen, and then we would do more of these two, where we're reabsorbing the bicarbonate in the proximal convoluted tubule. We're also reabsorbing sodium, so that would, be pulling water, raising your blood pressure a little bit too. And then out here in the collecting duct doing the chloride shift. Both cases reabsorbing bicarbonate, excreting, getting rid of the hydrogen. If we had the opposite situation, if we were too alkaline, we just don't want to do these anymore because that's just going to make us more alkaline. So we just stop doing those or slow them down. So we would secrete less hydrogen, reabsorb less bicarbonate. Okay, now let's just ignore those now, and we'll just go back to these guys. We just want to reabsorb sodium and water. Our blood pressure went down. We release ADH and aldosterone. Remember aldosterone too. Let's put this in here. That aldosterone comes from the angiotensinogen to angiotensin 1 to angiotensin 2, and that stimulates aldosterone. ADH is coming from your hypothalamus and being released from the posterior pituitary. Both are released when you have low blood pressure and you want to raise the blood pressure. So they're going to stimulate these carriers. So we reabsorb more sodium. Sodium passes into the cell in all cases. Sodium is then pumped out of the cell into the blood. Following the sodium will be water. This NAK2Cl carrier should look familiar to you from over here. That helps to set up the whole medullary concentration gradient to really reabsorb water from the thin segment of the loop. So all of these things are tied together. Okay, so that is a lot of information. It's a long video. Geez, sorry about that. There's only one more video. It's much shorter. So I'm going to end this one here. The next video will be about diuretics. You might want to watch this section a couple times. Reread those slides now that you understand those parts, or now that you've heard the explanation, and then come back and watch the last video, which will be about diuretics.